Hello and welcome back to another Applied Calculus lesson. In today's lesson, we're going to discuss section 4.4, and this is going to basically be an application section where we revisit a lot of the conversation we had earlier in chapter 4, notably talking about things like local and global extrema, inflection points, and essentially what we're going to try to do is use that information to learn how to maximize things in economics like profit, revenue, and things of that nature. So to begin with, we need to recall what it is profit, cost, and revenue are and how they're related to one another. And the way that we've discussed them so far, revenue is how much you make after producing, say, Q units. So Q is going to be our independent variable. Capital R will be our revenue function, capital C is our cost function, and then we defined what it means to have a profit function, P, that is pi, Greek letter pi, and of course a profit is going to be how much money you make minus how much money it costs to produce whatever it is that you are producing. So it maybe goes without saying that a business would be very interested in maximizing their profit. So that's what we're going to focus on today. To begin with, let's just start again with the notions of revenue and cost, draw a couple of pictures of what's happening, and see if we can't sniff out what it means to maximize profit. And we'll see how we can connect that to information we've already learned about. So to begin with, we're guided by an example. This example says, suppose that you work for a given corporation, and after looking over the books, you've been able to use a program like Excel to provide a large quantity of cost and revenue values for a variety of quantity Q. This is more or less how different corporations actually function. You have a huge data set, and then you can plot them as sort of some points on a Cartesian coordinate plane, and then you can connect the points in some sort of a continuous way to produce cost and revenue functions. So suppose you're given something that when you go through this process, you end up yielding something like this. You might recognize from a previous lesson earlier in the semester that we did this exact type of picture we're about to do, but the cost and the revenue functions were lines. That's a very simplistic type of model. In reality, the cost and the revenue functions don't have to be lines at all. For example, if we have our two axes, Q, the quantity axis, and dollars, the dependent axis, our cost function might be something like this. As our quantity increases from left to right, our costs might go up, and then might come back down, and then go back up again. Oops. Let's redo that. They go up, down, and back up again. This is perfectly possible depending on what it is that your company creates. Your revenue might be modeled by something that starts off pretty much like a straight line at 0, and then it just arcs continuously like that. So this down here is our cost function, this up here is our revenue function. This is a perfectly acceptable representation of a cost and a revenue function that you might run into. Maybe what we'll do here, given that I drew it all to the right, is we will try to move it a little bit to the left. There we go. Now, the real question we want to run up against is a question about profit. So, actually, we'll take this and we will see what we can do about moving it up a little bit as well. There we go. Profit, remember that profit is equal to revenue minus cost. So for example, if I looked at, say, we'll use a different color, this point in time, maybe this is Q equal to 40, notice that the cost of making 40 units is all the way up here, and the revenue after making 40 units is all the way down here. And so, if my profit function is revenue minus cost, then at 40 units, my cost is so much higher than my revenue, so my profit function will end up being a negative number. So this distance ends up producing a negative number for the profit, and so here the profit after making 40 units is actually negative. So this is producing a loss on the company. This can be contrasted, for example, when you move forward in quantity a little bit, and you find that maybe for this number of units, maybe this is, I don't know, 120 units, we find that our revenue at 120 units is all the way up here, and the cost is down here. So in this case, we're actually making more money than it costs to produce 120 units. So here, we're actually making some good profit. So right here, we're actually profiting. So here, pi of 120 is positive. So in this case, our company is gaining. So this gives us an idea of how this works. It would seem that as long as revenue is above cost, which it is in this section, as long as revenue is above cost, we're going to be making a profit. Whereas over here to the left, when revenue was below cost, we were at a loss. So if our objective in this section is how do we maximize profit, observe that if we extend our x-axis just a smidge to the right, there we go, what we might observe is that I could also turn around and take a look at maybe over here, we could have a different quantity. Maybe this is 170. And what we notice of here is that there's the revenue, there's the cost. This, again, is the profit. So this is a profit, and this is a profit. So what we want to know is, where is the largest profit? Well, the profit that this company actually makes is the length of these purple lines. So this purple line is a little bit shorter than this purple line. So therefore, apparently, this company is gaining more money at 170 than they would be making 120 units. So we can sort of see by this argument that if we wanted to maximize profit, we need to find the magic point where the distance between the revenue function and the cost function is largest, which looks to me like it'll be somewhere around the middle here. So probably it's going to be somewhere around, I would say, right here. There's that revenue, there's that cost. It would probably be right there. So I would say, just by inspection, that based on our picture, this right here is the moment of maximized profit. And based roughly on what I've written down here, we might observe that maybe this is, say, 150 or something like that. So this is how, if you're given two graphs of revenue and cost, we might deduce where the maximized profit might be occurring. So if we wanted to write down sort of exactly what it is we're observing, we might write down the following. We might observe that according to the graph's profit is maximized when the distance between the revenue function and the cost function is maximized. Of course, parenthetically, with the revenue above the cost. That was an important caveat. And according to what we've seen in this example, this occurs at approximately Q equals 150. So this is maybe a way that we can deduce how to maximize profits with a picture. But the question is, how do we do this with calculus? How do we do this with the techniques we've been learning so far in Chapter 4? That's a really good question, and that's what we're going to address. What we're going to do at the top of the next page is we're going to zero in on this maximized profit right here. And we're going to zoom in on that and make it a little bit bigger. So maybe what we'll try to do is we will cut this and see if we can't bring that with us. Here we go. Make it a little bit bigger. And here we are. Now, if we erase, oh, don't want to do that. We'll keep that stuff to the left. So what we've done is we've zoomed in on the part of the graph where the profit was maximized. Now, there's a really important observation we can make that's going to relate all of this to the calculus that we've been investigating so far. Look at the 2 points right there on the revenue and the cost graph where we identified maximized profit. There's a really, really important observation we can make. That observation is that if I turn around and I build the tangent line at those points for their respective functions, the tangent line for R might look something like that. And the tangent line for C might look something like that. The key observation that we can make, of course, is that these two tangent lines right here are parallel. What does that mean? Well, remember that slopes of tangent lines are literally just derivatives. So, what we've deduced here is that not only are the slopes of the tangent lines of R and C parallel, this implies that if profit is maximized at a point, then their derivatives at that point have to be equal to each other. And so this is how we're going to take our picture observation and we're going to turn this into a calculus observation. What we've just deduced is that, in fact, maximized profit occurs when your derivative of revenue and your derivative of cost are equal to one another. But remember, profit is just revenue minus cost. And we note that the derivative of a difference is the difference of the derivatives. So we can reinterpret this statement as, if profit is maximized at a point, then by moving cost over to the left-hand side, we would end up with R prime minus C prime is equal to 0, or equivalently, profit differentiated is equal to 0. Now, you might recognize what it means for the derivative of a function to be 0. What this means is we have candidates for critical points, which of course, according to the content we discussed in section 4.1 and 4.3, means that this is of course related to local and global extrema. So it sounds like all of this is sort of tied together in a really nice way. Now, let's bring back some more vocabulary that we've discussed in the past. We were going to recall that anytime the derivative of an economic quantity is discussed, we usually refer to that as its marginal quantity. So for example, if pi is representing cost if pi is representing profit, then marginal profit would be pi prime of q, or there must be a typo here. Let's go ahead and fix this. What we might say is that marginal cost would be c prime of q, to make that consistent. So then what we've deduced right now is the following type theorem, that we can maximize or minimize profit in the following way, that the maximum or minimum profit occurs when either the marginal profit, which we might remember, of course, marginal profit based on what we just talked about is pi prime of a value, say p naught, is equal to 0. Or if I want to, I could use this representation from up here, and I could interpret this as when marginal revenue is equal to marginal cost. Now, as we noted before, this is, of course, eerily familiar, because what we're seeing now is that the maximum or minimum profit seems to occur at critical points of the profit function. Now, just as we discussed in section 4.1 and 4.3, this does not imply that every single critical point is a max or min, but that if you have a point of max or min profit, then it must have occurred at a critical point. So for me, I like to approach maximizing a corporation's profit in exactly the same way we approached it in sections 4.1 and 4.3. But with these alternate interpretations, there are many different ways one can do this. To see what I mean, let's take a look at an example. Here we have an example where we want to find the quantity which maximizes profit if the total revenue and total cost are given to us as these two functions. Now, we have to be careful a little bit here. Well, not that we have to be careful, but we should take note that in the previous lifetime, when we were doing this in a few chapters ago, our revenue and our cost functions were lines. Our cost here is still a line, but our revenue is quadratic. So sort of the old ways of doing this have gone out the window. We now need these calculus-based approaches. Additionally, we've imposed a restriction. We can either produce as little as no units or as many as 1,000 units. So in this example, we have a restriction on the input variable. And what that means is that instead of just finding local maxes, we're actually going to be trying to find global maxes. So this is where section 4.3 content becomes important as opposed to just section 4.1 content. So let's go ahead and make a start and let's see what we can come up with. Let's write down what our goal is. So we need the global max of the profit function, which remember is just the revenue function minus the cost function, on Q living somewhere between 0 and 1,000. Well, to do this, I'm going to start by finding the critical points of my profit function, which involves differentiating it. So we might start by writing down what the profit function actually is. Again, the profit function is revenue minus cost. What does this turn out to be? Well, the revenue is 5q minus 0.003q squared minus the cost. I'm going to open up parentheses here to make sure I distribute this negative. 300 plus 1.1q. And here, if I distribute the negative and then I simplify, I should end up with negative 0.003q squared plus 3.9q minus 300. Now we're going to find the critical points. To do that, we have to check when the first derivative of the profit function is either undefined or 0. So we're going to start by setting pi prime equal to 0. which if I were to differentiate this function I'd gotten above, I would of course get negative 0.006q plus 3.9 now equal to 0. And if I solve that for q, I'm going to end up getting 650. So this handles the case when a critical point might come from the derivative being 0. Observe that the derivative is never undefined because it's a polynomial. So what we'll say is that since pi prime of q is never undefined, q equals 650 is our only critical point. So now we have a critical point, but of course we don't yet know whether this critical point is going to yield a local min or a local max. We have to apply the first derivative test in order to determine that. So we're going to draw a real number line. We're going to put our critical point 650 on there. Above we're going to have the derivative of profit. Below we're going to have profit. And what you'll notice is that if you plug in test points to the left and to the right of 650 into that derivative function, to the left you'll end up with a positive, and to the right you'll end up with a negative. What that means is that my profit is increasing for a period of time and then decreasing. And that implies that this magic critical point, Q, which is 650, is a local max. Remember that the first derivative test only tells you about local maxes. We still don't yet know if it's global. So that's the next question. Is it global? To do that, we have to check it against these endpoints 1 and 1000. So what we do is we take 0 and 1000 and then the critical point 650, and we evaluate them at the original profit function and determine which one is the highest. So we need to check out what pi of 0 is, we need to know what pi of 650 is, and we need to know what pi of 1000 is. Well, if you plug them in, what you end up getting for 0 is negative 300. What you end up with 650 is you get 967.5. And for 1000, you'll end up with 600. Now, it is important to note that these are dollars, so I should probably add units where I can. So that's negative $300, positive $967.5, and positive $600. So what we find here is that Q equals 650 units produces a global maximum of $967.50. So all of the information we've done here is very reminiscent of what we talked about in sections 4.1 and 4.3. Particularly 4.3 because here we were given a restriction on units, which means we have endpoints, and so we have to do this final step at the bottom. But this is how I approach determining maximum profit for these types of economics flavor questions. The next example that we're going to run up against is example 3. It's very similar. We're given a revenue function and we're given a cost function, but we're not given any sort of a domain restriction of how many units we can produce. So in this case, it's sufficient to simply find the local max to maximize profit instead of having to do the global max step. But the process is going to remain the same. For starters, we're going to have to write down what the profit function is. Remember, of course, pi of q is just r of q minus c of q. In this case, it's apparently 500q minus q squared, that's r, minus the cost function, which is 150 plus 10q, which again, if I distribute the negative, I'll end up with something that looks like negative q squared plus 450q minus 150. Now we need to find critical points. So we're going to find critical points. We might again note, well, let's start by taking the derivative. We're going to start by doing pi prime of q equal to 0. But what is pi prime? If I differentiate this original profit function, I'm going to end up getting negative 2q plus 450 is equal to 0. And if I solve for q, I get q is equal to 225. Then we might note that since pi prime of q, again, much like in the previous example, pi prime here, this is just a line. Of course, a line is never undefined. Since pi prime of q is never undefined, q equals 225 is our only critical point. Now, we don't yet know that this is the point of maximum. We still have to determine that by applying the first derivative test. So we're going to plug in 225 onto our real number line. We'll have pi prime above and pi down below. And again, if you plug in some values to the left of 225 into the derivative, which is this line, we'll end up with a positive. For example, you could plug in 0. Plug in 0 here, you'll get 450. That's clearly a positive value. And if you plug in something to the right, you'll end up with a negative, which means our profit is increasing and then suddenly decreasing. So what this concludes is that q equals 225. Not only is it a local max, but since there's no endpoints to consider, we know that 225 produces maximum profit. So again, it's more or less the same exact process. Now, the next page is going to encounter a slightly different set of circumstances. In this final section, we encounter maximizing revenue. Now, in some instances, it turns out that how much you make, or rather how much it costs to run your company, does not actually depend on the number of items or the number of quantities made. A really good example of this is a city bus company with a fixed schedule. This company runs buses on a fixed route and a fixed schedule. They don't really care. It costs the same amount to run their bus whether 2 people get on the bus or 4 people get on the bus. So for them, they maximize profit when they maximize revenue. The cost is fixed and it doesn't change. So there are times when you'll encounter problems like this where instead of having to maximize that profit function, you're only maximizing the revenue. So an example of that is as follows. This is a classic example we're running up against, and in this case, we're going to introduce the notion of a demand function. So here we have a whitewater rafting company, and apparently they sell half-day trips for $80. In particular, they know that if every day they're open, they're going to attract 300 customers. Now, those 300 customers are only attracted for that $80 price tag. They know, for example, that in order to beat competitors, if they decrease the cost of their trip, then they're going to attract more customers. And based on some prior data, they determine that for every $5 decrease in their costs, they attract 30 additional customers. So to begin with, basically what their goal is okay, well, how much should they be charging if they want to maximize how much money they're going to make? That's really the question. So to begin with, we need to come up with what's called a demand equation. In this case, what kind of demand are they trying to satisfy? They're trying to satisfy customers interested in going on the trip. So for our purposes here, the demand function is the number of customers. And in a very confusing way, whenever you talk about demand functions, usually demand is the number of customers being allocated dependent on some sort of a price. Price starts with the letter P, and so usually you let price be P, and then the demand function, the output, the number of customers, tends to be Q. Despite the fact that in the cost revenue functions we've been doing so far, Q tends to be the independent variable quantity. In demand equations, in demand problems like this, Q tends to be the dependent variable because that represents what the demand or the number of customers as a result of price. So it's a little confusing that we use the same letter in two different places. But this is sort of how the general community does it, so we have to get comfortable with it. So for here, we're going to use let the demand equation represent the number of customers, say Q. And just to be clear, this demand function is a function of price that we're going to call P. So it's going to be Q, and if P changes, then Q will change. We have to figure out, based on the information provided, what the demand equation is. That is, we need to note that Q is going to be equal to something, and that something has to be dependent on P. This is where you have to think a little bit critically. Q is representing the number of customers. Well, the number of customers starts at 300. So we know we're at least going to start with 300. And then it says that every time we change the price, we're going to attract customers. So the number of customers will then be increasing. And it's going to increase by 30. So we're going to add 30 every time something happens. What is it that happens? It's every time there's a $5 decrease. So what that means is we want the price to start at 80, and if it goes down to, say, 70, we want this quantity in these parentheses to be a 2. That's what we want right here. We want this thing to be, if, say, the price is $70, we need this to be a 2. Because if it was a 2, then we would get 2 times 30, which is 60. And yes, that satisfies the original problem, is that if we've gone down by 2 $5 decreases and we go to 70, we need to go up by 30 customers twice. So this would be 300 plus 30 times 2. So what is it that has to be in here such that if I charge $70, this overall parentheses is a 2? Well, it turns out the right way to proceed is that we're going to take 80, the original amount. We're going to subtract off the new price, which is going to be P. And if P is 70, we'll get 80 minus 70. That's 10. How do I get from 10 to 2? I divide by 5. And there we go. This is going to take the original price, subtract off the new price, cut it up into however many increments of 5 that difference occurs, and then give us 30 customers for every $5 decrease. Now, I could simplify this a little bit and get Q is 300 plus, let's see, 30 over 5, that's a 6, times 80 minus P. I could even simplify that further, and I could turn that into, say, if I distribute the 6, I could get 780 minus 6P. Now, I should note here that every time you build out an equation like this, you should test it. Just like I did right here, you should test it. So what you should check is that Q of 70 equals 360. if that's true in this case, then you probably have the right function. And so you should always be testing whatever you come up with. Now that we have a demand equation, now the question is, what is the revenue that this company has? Well, remember, the demand equation is the number of customers. So the revenue is, of course, going to be the price of each ticket times the number of people buying the ticket. But Q has that representation. That's Q. So revenue is P times 780 minus 6P, which if I distribute the P, I'm getting 780P minus 6P squared. That's my revenue. Now that I have revenue, I can now maximize it. So how do we do that? We do it in exactly the same way we've been doing it this entire time. So what are we going to do? We're going to find critical points for revenue. How do we do that? For starters, we're going to do R prime of Q is equal to 0. That occurs if and only if differentiating the revenue function will give me 780 minus 12P is equal to 0. But of course, if I solve that, I'm getting P is equal to 65. Again, since R prime of Q is never undefined, the price 65 is our only critical point. I don't yet know that it's a max or a min, or neither, so I do the first derivative test. I put R in the bottom. I put R prime up top. That's 65. And again, if I look at the derivative right here, if I plug in, say, 0, I'm going to get just 780. That's a positive. And if I plug in something greater than 65, I'll get a negative, which means revenue is switching from increasing to decreasing. So what that tells us is that P equals 65 is a local max. However, there's no endpoints on price in this problem, so therefore a cost, sorry, we shouldn't use the word cost, let's say a price of $65 maximizes revenue. And so this is a problem that helps us learn how to apply these techniques to not just maximize profit, but in this instance, maximize revenue. Additionally, in this problem, we also discussed some new techniques we have up here for actually deducing a revenue function from a given word problem. All of the other problems we did in this lesson they gave us our revenue and our cost functions, and then we had to just find profit from there. Here we had to actually create it from scratch. This is going to conclude our content in section 4.4. So with this knowledge, we have enough to tackle some of the homework problems and continue mastering the techniques that we learned as they relate to local mins and maxes, global extrema, and things of that nature. Thank you all for tuning in, and I will catch you all in the next one.